Hi, this lecture is a introduction to thinking about resistive materials. Yeah, so here we go. Before I talk about materials, though, I'd like to point out that we can actually think about electric current or current density in the situation of empty space. So we're thinking about vacuum, right? So nothing is in there except for I drew it as a little cloud, like a little cloud of a grouping of charged particles. And these charged particles are not in any material. They're just sort of like by themselves. Of course, they're going to repel each other if they're all the same sign of charge. But I'd like you to consider what happens to each of the charges, not because of their sort of mutual repulsion going on, but because they're actually in a background, in the vacuum, with an electric field. So I've drawn these electric field lines. They go from this conductor over on the left side over to this conductor on the right-hand side. This electric field is because, right, so remember electric field points from positive charge to negative charge in general, but also it actually points, yeah, I'll just do that. So I'm going to put some negative charges over there. So the field lines go from a positive charge localization to a negative charge, and if this little cloud of free charges is a bunch of positive charges, right, they're going to accelerate across the gap. And because there is strictly vacuum, vacuum offers no resistance. Vacuum is just free, empty space. So the only thing accelerating these charges is the electric field that's in the background, in the vacuum. So you can describe this little grouping of electric charges in terms of, and this is sort of alluding to a previous video, a number density. So it's the number of charge carriers per volume multiplied by the charge of each charge carrier. So I just mocked up a value. It's 5 microcoulombs per meter cubed, right? That could sort of describe the number or the charge carrier density of this little cloud. So the reason I wanted to use this is because in one of the previous videos, I told you how to model the relationship or think of a current density in terms of a charge carrier density multiplied by what's called a drift velocity, where the drift velocity is the velocity of each of these little charges. So the little drift velocities, right, are velocity vectors. And this modeled the connection between thinking of current, which actually it's current density, and charge carrier density and drift velocity. And we know what electric field does. So we've got this background electric field. There is going to be a force on each of these little charges by this electric field. And it turns out that it's only one force because our vacuum offers no resistance. There's nothing in the way. There's nothing to run into. There's no friction. There's no anything else. It's empty, empty, empty space. Which means that thinking in terms of the electric field only ever tells us, right, according to Newton's second law, if we have a force, we can describe acceleration. Acceleration tells us how velocity changes. And in this case, we expect that the drift velocity only speeds up, right? Grows. So the drift velocity grows in this scenario. And you would say then if the velocity is growing and this isn't changing, then that means that the current density is growing as well, right? So the current density is getting bigger in time. The current is the integral, right, of the current density. And so if the current density itself is growing, then that means that the current itself, right, the current, which is the thing we know how to measure with an ammeter. So ammeters measure this, right? So that means that we would notice that the current is growing. It's getting faster and faster and faster, right? And I'm talking about if I was to measure the current of charge, say, across this sort of imagined boundary, right? We're going to watch all of these charges race across and essentially speed up. Okay, but a point that I want to make is the reason that, so we're going to get acceleration, right? Acceleration of all the charges, which means the current is growing and growing and growing. And what this means is that we don't get a steady current. When you go, though, and build a circuit, so I've drawn a little circuit diagram right here. I've got a little battery, right? And remember that the long side of the diagram of the battery is meant to be the high potential side, and the short side is meant to be the low potential side. And the high potential side tends to have the positive electric charge. The low potential side has the negative electric charge. And so in this material, this black material, there is going to be electric field, and it's going to point from the high potential or positively charged side towards the negative side, right? And you have had some experiences in your lab with an idea called Ohm's law. Ohm's law says that the current that you get is proportional to the voltage applied across your conductor, right? And that constant of proportionality is referred to as the resistance. But the reason that I bring this up is whenever you do this experiment, right, you have a resistive material, you have some sort of material, when you have a steady value of voltage, all you ever get is a current that's constant. That is, your current is not growing in time, even though your voltage gives you an electric field, and the electric fields accelerate charge, right? So when current flows in a conductor, if the potential difference is steady, then the current is also going to be constant in time. That means that not only is there going to be this electric field force, right? You got this little electric field force, there must be some sort of resistance. And I'm going to put this little symbol for resistivity. So that means that as the charges go through this conductor, they're going to meet resistance, which is going to cause the current to be steady instead. All right? So what I've done is I've drawn a picture of this resistive material between these two oppositely charged conductors. So we'll say that the conductor on the left-hand side has the positive charge, because this is where the electric field lines are coming from. And the conductor on the other side has the negative charges, so the field lines are going from positive to negative, just like you're used to, right? And when you look in here, so please don't forget that it's the negative charge inside of a conductor that actually is going to be moving with the drift velocity v sub d, right? So each of these little things is moving. But as it moves, right, so these negative charges feel a force in the opposite direction of the electric field direction, which is shown in blue. So, right, they're going to be accelerated leftward by the electric field, but we're going to come up with a model of resistance, or a model of what's referred to as the resistivity of a material, right? So that's what I'm going to describe next, is this thing called resistivity. The symbol that I'm going to use for resistivity is called rho. So the way you pronounce this letter is rho. And it can be confusing because actually this symbol is often used for mass density and also charge density. But in this particular case, we're using rho to symbolize resistivity because of the sort of phonetics of the letter, right? Resistivity and rho. It's the same letter R, right? But we're going to use the Greek symbol. And here is our model. So I'm going to put it in a box because it's important. What it says is that inside of a resistive material, you're going to get a current density that is proportional to the strength of the electric field within the material. So this electric field that I'm alluding to is the electric field associated with the blue lines. It's the electric field set up by, if you look at this kind of looks like a capacitor. It's actually not a capacitor in this case. In this case, it's called a resistor. But you've got a high potential and a low potential, and because you have a difference in potential, you're going to have electric field. And the electric field that I'm talking about, it sits right here. It says that the current density of how these electrons move within the material is just proportional to the electric field by this thing called the resistivity. It's actually 1 divided by the resistivity. So if you have a very resistive material, then 1 divided by that large resistivity is a small number. And that small number times even a strong electric field gives rise to a small amount of current density. But if your resistivity is 0, that's the situation of a perfect conductor. 1 divided by 0 is infinity, and the current density that you're going to get is infinity if you have a infinitely good conductor. But real materials, including copper and gold, right, which have very, very low resistivities, it's not 0 resistivity. So this is our model. It just models the current density being proportional to the electric field, where the proportionality is called the resistivity. It's 1 over the resistivity. And we can do a little bit of physics. And the physics that I'm talking about is just thinking about the units. What are the units of rho? So rho, if you look at its place, if you, in a sense, solve for it, right, you'll put the rho up to the top on the left side, and then you'll imagine dividing by j. But remember that you can't divide by a vector. You don't know how to do that. I mean, you can come up with ways to maybe define such a thing, but it's not what you think. It's not simple. So in order to solve for rho, what I'm going to do is take the magnitude of both sides, right? If j vector equals 1 over rho e vector, then j magnitude equals 1 over rho e magnitude. And e magnitude and j magnitude, those are scalars, right? They're not vectors, and you can divide by a scalar, no problem at all. So that's what I did. I divided the scalars. So the scalars have the units. So the scalar E, right, electric field, is force per charge. So newtons per coulomb is the SI unit. And J, current density, is not current per volume, it's current per area, right? Current, SI unit, is the ampere, and area, SI unit, is the meter squared. So if you just do a little bit of algebra, right, the units, right, so you have newtons per amp and then meter squared per coulomb, right? You have to remember how to divide fractions. I'll just remind you, if you take a number A divided by B divided by C divided by D, where the instruction is to divide A and B first, divide C and D second, and then divide the two divisions, right? So can you see the order of operations going on? This is equal to A over B times D over C. You just multiply by the bottom inverse, right? That's what I did over here. Okay, so I've got these units, but let me remind you of something. Ohm's law set us up to have what's called a resistance, capital R. And capital R's unit is the ohm. And the ohm is an SI unit of resistance. It's not an SI unit of resistivity, but of the resistance of a circuit device, of a resistor, right? And omega is defined as the volt per amp. This is the definition of omega, the volt per amp. So what I'm going to show you is how to rewrite this thing called the resistivity in terms of ohms and meters, actually. So this is true right here. The Newton meter squared per amp coulomb is also known as the ohm meter. So let me show you that real quick. So the Newton meter squared per amp coulomb is the ohm meter. Let's prove this, right? So let me draw this more clearly. So it's the ohm meter. This is called, that letter's name is omega, and it's used for as a symbol of the SI unit of resistance called the ohm, right? So the ohm is the unit of resistance, not resistivity, right? You see these two words, they're different because they indicate different things. We'll talk about resistance a little bit more in a subsequent video. We are talking about resistivity right now, right? Okay, so let's look at this. What I'm going to do is I want to prove this, right? So question is this true? Is the ohm meter equal to the Newton meter squared per amp coulomb? And I'm going to assume that it is. So what I'm going to do is divide both sides by the meter, right? And I've got the omega left. And omega, I know omega as the volt per amp. That's what I showed you up here. This is the definition of the ohm. It's the volt per amp, right? So here's the volt per amp, right? Because we divided away the meter, and we've got a Newton meter per amp coulomb. So what does this look like? So the Newton meter is actually also the joule, right? Remember that Newton's meters, it looks like force times displacement. And if you apply 1 Newton for 1 meter, you get 1 joule of work, right? It's an energy unit, force times distance. So the Newton times meter that I have left over is the joule. And another thing is the volt is the same thing as the joule per coulomb, right? The volt is an amount of work per charge. So the volt is a joule per coulomb. I'm hoping that this feels like review. So anyways, I've got the joule, I've got the amp, and I've got the coulomb, right? And the amp is common to both on the denominator, and the joule per coulomb is the volt. So my assumption was true because I just showed that the volt equals the volt, right? So that was a little bit of an exercise just showing you what the units do, right? Reminding you of that all of the stuff that you've been learning since the beginning, it all is important, right? All of this stuff is accumulating as a knowledge base. So that's just a quick thing. So resistivity is going to have units in tables, right? If you go look up values for resistivity of different materials like gold and silver and copper and steel and even air and diamond, right? You can look up the resistivity of anything. So there is another designation of the resistivity of of a material, and it takes sort of the optimistic viewpoint. So resistivity tends to be kind of like a pessimistic view. Sigma represents conductivity. Conductivity is the inverse of resistivity. So this is called the conductivity. It's the optimistic point of view, right? POV. Optimistic point of view. That's a joke. It's not science. So, yeah. So what I've showed you is a model that connects the current flow at a place in a material, right? This is a coordinate inside of a material. This is the resistivity at this coordinate, and this is the electric field at the same coordinate. So you can have a current density that might change because the electric field is different at different places. Or the current density could change because maybe the resistivity is different at different places, right? But this is our simple model. It's a model. And you might ask, is this correct? And the answer is most definitely it's not perfect. There are better models, but they're going to be based on trying to figure out how to represent the resistivity. Yeah, so it turns out actually that the resistivity can be temperature dependent, which is something I'm going to describe in a following video. So T for temperature. Okay,